All right, I'm gonna work through the chapter 11 FRAPPY question for you guys here now, in order to get ready for your test this Friday. So let's read it and get to it. Two stat students want to know if including additional information in a survey question would change the distribution of responses. To find out, they randomly selected 13 teenagers and asked them one of the following questions. 15 teens were randomly assigned to question A, 15 were assigned to question B. So let's read the questions. Question A says, when choosing a college, how important is a good athletic program? Very, somewhat, not that important, or not important at all. Here are our 5 choices. B, it's the second question, they rephrased it, said, it's sad that some people choose a college based on its athletic program. When choosing a college, how important is a good athletic program? And then the same 5 choices. And we talked about early in the year about the problem of leading questions. This is their study here is trying to figure out, right, well, we've asked this leading question and kind of painted sports as the negative thing, or a not great reason for choosing a college. So they're leading respondents to a certain answer. The question is, in this problem, we're going to actually try to do a statistical test to see if that leading question actually makes a statistical difference in the results. So that's what we're going to look at, if we can do a test to see if there's actually a difference between these two distributions. So the table below summarizes the responses to both questions. For these data, the chi-square test statistic is chi-squared equals 6.12. All right, so here is our table of observed counts. And let's go ahead and look at the problem as it comes. It says, state the hypotheses that the students are interested in testing. So first, our null hypothesis. You'll notice that this question is broken down into pieces, so we don't have to do the full state plan to conclude on this one. We can just answer the pieces as they come. The null hypothesis is that there would be no difference in these two distributions. So our null hypothesis could simply be the true distribution of responses is the same in both questions. So we could say the distribution of responses, or distributions of responses, are the same for both questions, right? That's the null hypothesis, that there's no difference between the two. Our alternative hypothesis would simply be that they're not the same. Okay. That's really it. That's all we need to do here in that first part. That's a nice, easy first part. State the hypotheses. In case you were concerned, you will not lose points for spelling on an AP Stats exam, unless your spelling is so bad that it changes the meaning of your sentence, but misspelled words will not cost you anything. All right, so now we can go to part B. It says describe a type 1 error and a type 2 error in the context of the hypotheses stated in part A. Okay, you'll notice too here, in this question, a lot of times when they ask about type 1 and type 2 errors, they'll ask for the consequences of those errors. In this case, it doesn't say that explicitly, so we just want to say what a type 1 error is, and we won't have to get into any consequences of it. Remember, type 1 is falsely rejecting the null, which means here we would reject the null and say that there is a difference in the two distributions, when in fact there is not a difference in the two distributions. That would be a type 1 error, is falsely rejecting the null. So this would be incorrectly rejecting the null. In context, that means we would conclude that there is a difference in the two distributions. When in fact there is not. Or we could say when the distributions are the same. Okay. Type 2 is incorrectly failing to reject the null. Okay. So type 2 would be incorrectly failing to reject the null. That means that we would not reject the null when in fact it is false. So we would conclude that there is not a difference, or excuse me, we wouldn't conclude that there is no difference, right? We don't accept the null, but we would fail to reject the null. Okay, so that means we would not find convincing evidence of a difference. When in fact there is a difference between the two distributions. Okay. And again, they don't ask us for consequences of that, so we can just leave it as that right there. We conclude, type 1 is concluding that there is a difference when there is not a difference in the two distributions. Type 2 is failing to recognize that there is a difference in the two distributions. Part C, this is a good one here. It says, for these data, explain why it would not be appropriate to use a chi-square distribution to calculate the p-value. If we look at the context here, we're clearly comparing a distribution, two different distributions on categorical variable here. The categorical variable being opinion of or importance of sports program in choosing a college. So we definitely are comparing the difference in distributions between two populations on the same categorical variable, which is a chi-square test. But if we were going to actually execute that test, we would need to make sure we check our conditions. So when we get to this question C, what we really need to be focusing on is, are all of our conditions met, right? That's really what we're getting at. It definitely is the right setting for a chi-square test, but on these data, are all of our conditions met? So the random condition is met for sure. It says they randomly assign the teenagers to their question. The 10% condition would certainly be met. There are well over 300 teenagers. So we need to look at the normal condition, which is the large counts condition. And the large counts condition says that we need all of the expected counts to be greater than 5. Okay, so we would have to compute the expected counts. I've already put the observed counts into our calculator here, so we can just quickly do the test, do the chi-square test. That's not what I wanted. Sorry, stats test, that's why. Stat test, I want to do a chi-square test for goodness of fit. I'm trying to see if the distribution of people from question B matches the distribution from question A. And our observed list. Sorry, I misspoke. We wouldn't be doing the goodness of fit test. We want to do, we're doing a test for independence here. We're trying to determine, is there a relationship between the two variables? One variable is how important you think college or sports programs are in deciding for college. And the second variable is the phrasing of the question. Does the phrasing of the question influence the way we respond to it or influence our opinion? So this is a test for independence, or the two-way test. And then in the two-way test, we would pick our observed matrix, and then there are our expected counts. Or excuse me, there's our chi-square. This is consistent with the information given in the exam, but we're not really concerned about this. What we want is the expected matrix. So now we can go to the variable button and find our expected matrix. And here are all of our expected counts, okay? Now remember, what we're really interested in this part of the problem is, can we do the chi-square test? Now I know I've already executed the test on the calculator. The point is it a statistically viable test? And that depends on the large counts condition. The large counts condition requires, okay, the large counts condition requires that we have expected counts all greater than 5. So in this case, if we look at our expected counts, not only are they not all greater than 5, they're in fact all less than 5. So this doesn't even come close to satisfying the expected counts or the large counts condition. Okay, large counts is not met here because expected counts are all less than 5, so the large counts condition is not met. It took me a minute to get through all that and explain all of that, but that's really all that we're looking for, is a really basic, straightforward answer here. The large counts condition is not met, so we wouldn't be able to do our normal computations and so forth. It would be, you should definitely include the expected counts in your answer to verify what we're talking about here. Is killing me. Why would that move over there? Alright, so expected counts is not met, or expected counts are all too small, so we didn't meet the large counts condition. That's why we can't use the chi-square test. Part D asks to estimate the p-value. 100 trials of a simulation were conducted, assuming that the additional information didn't have an effect on the response to the question. In each trial of the simulation, the value of, so again, they're assuming that the null hypothesis is true. In each of the trials, based on the null hypothesis, the value of chi-square was calculated. These simulated chi-square stats are displayed in the dot plot below. So each of these dots is one test where they simulated these circumstances, 15 students on each group and whatever, and computed the chi-square based on a random data. So in these 100 samples, we can see 6.12 was our chi-square value in the question right at the beginning. From this data, we get a chi-square value of 6.12. What they did is randomize this data 100 times and found all of the corresponding chi-square data. And each dot is a different chi-square. Based on the results of the simulation, what conclusion would you make about the hypotheses stated in part A? Well, if we look carefully here, 6.12 is right around right there. It's a little bit hard to tell whether these values are above or below 6.12, but even if we're not sure about those, all of these are definitely greater than 6.12. And there are 3, 6, 9, 12, 15, 18, 20 values in there. So those 20 values, and I think in the answer key, the scoring rubric, they count 24, so they count those values in the group. But either way, we get 20 groups, or 20 of the trials that had a chi-square value greater than what we saw in the actual example data that they had. Okay, so this means that 20% of trials had a greater chi-square value okay, so our p-value would be approximately 20%. Okay, and so based on our simulation, we would estimate the p-value to be about 0.2. That is to say, there's about a 20% chance that we would expect chi-square value at 6.12 or greater based on random data. If there were no difference in the two distributions, there's a 20% chance of getting chi-square as large or larger than we did in our example, which gives us a p-value of 20%. And so that's greater than any reasonable alpha level that we've picked, so we can say because our p-value is greater than say 0.05 as our alpha level, we will fail to reject the null hypothesis. There is not convincing evidence of a difference in the two distributions. Okay. So this is kind of a weird free response question in that you didn't actually have to do the significance test, or that wasn't really what the question was. They kind of broke it down into pieces for you, but you'd still basically do all the key pieces. You did state the hypotheses. You did end up checking the conditions. You kind of had to perform the test to get the expected counts, and then you still did compare a p-value at the end. So you basically still did work through the whole test, but just in different pieces and in a weird way. So there's a good example of a type of question you might expect on the chapter test this Friday, and that's all for now.